Section 6.3 has to do with proofs and disproofs. And why don't we just take a look at the example that they give right at the beginning of the section. They say, consider the following property. Now, I'm not sure if we've introduced this concept over here. A minus B, this is sometimes called the set difference. And what this means is X is contained in A minus B if and only if X is contained in A and X is not contained in B. So if we wanted to draw a picture of that, if that's A and that's B, A minus B would correspond to this area right over here. It's what's in A and isn't in B. Now, let's get back to our problem here. We're asked, is this true or not? I'll put a big question mark here. And the problem that you have in mathematics when you don't know is the following. If this statement is true, you have to provide a proof. And providing a proof is not always easy. On the other hand, maybe this is false. Now remember, for it to be false, it means that you just have to come up with one situation in which it's false. But that sounds a lot easier than it may be, because there are infinitely many different situations that you can consider. Well, let's just draw a couple of pictures and see what we can do with this. If I come over here, and if this is A, and that's B, and that's C. So here's A, here's B, here's C. And it might be a good idea here to try a couple of different colors here. So first of all, let's pick red. And I'm going to draw A minus B. I'll draw that in red. So whatever's in A and isn't in B, that's going to correspond to this area right over here. Okay, notice that I've left this part right here out because that part is in B. And now, why don't we come over here and pick a different color. Okay, so now what I'm going to do is I'm going to do B minus C in this greenish color. So B minus C actually corresponds to this. So remember, this is everything that's in B that isn't in C. Right over there. So this does not include this little piece over here. So if I were to talk about A minus B union B minus C, it's everything in here that has color in it. Okay, so now the question is what is A minus C? And again, we go to a different color. Why don't we pick blue? Well, whatever's in A that isn't in C is going to be all of this. Just like that. Now, remember, this part over here is all the red and green. This part over here is all the blue. They're not the same. So in general, this is false. Now you have to be careful here, because let us suppose that I had drawn a picture where it was true. Does that mean that this statement is in general true? No, it doesn't. It just means that I haven't provided a good counterexample. So the problem in disproving something is you've got to find the counterexample, and the counterexample could take you a very long time to find. If you're given some statement and you don't know whether it's true or not, the first thing you should do is probably draw a few pictures. Now you might consider a different picture here. You might consider maybe they disjoint sets. Or maybe only two of them intersect. So I might have a situation that looks like this. Here's A, here's B, here's C. You have to consider lots of different possibilities. Now, the other thing that we could do here is we could actually put some numbers in here. We could create different sets. We don't have to just use pictures. For example, I could come over here and I could say, let A equal 1, 2, 3, 4. And I could say, let B equal 3, 4, 5, 6. And I could say, let C equal 8 and 9. Now, in this situation over here, we can see that the intersection of A and B is not empty, but we can see that A and B have nothing in common with C. So this situation right over here very much seems to correspond to this picture right over here. Now, if I go ahead and I calculate things, A minus B in this situation would be 1, 2. And B minus C, well, they have nothing in common, so B minus C would just be the set B. And we could see that the set that A minus C, well, they have nothing in common. So let's see, I'm running out of room here. I think I can squeeze it in over here, A minus C would just be the set A again, 1, 2, 3, 4. And we could see that A minus B union B minus C would be the union of these two sets, which would be 1, 2, 3, 4, 5, 6. But A minus C is 1, 2, 3, 4. So this actually provides explicit sets that provide us with a counterexample. Let's consider another example, but before we do, I want to talk about something called the set difference law. This is one of those theorems, if you go back, what is it, to theorem 6.2.2, where there were a page full of them, page full of theorems. This is one of them. We're going to use this one, so it might be useful to discuss. And it just says something like the following, that, A minus C is the same thing as saying A intersection C complement. Now, we can draw a picture of that that convinces us of that. We'll also prove it. So let's come over here. Here's A. Here's C. So here is A, and here is C. And let's consider, if I wanted to prove this just by picture, this over here just says that X is contained in A, and X is not, or X is contained in A and X is not contained in C. Okay? So we come over here, if this is C, okay, C complement is going to be all of this. Okay, you can imagine taking this circle C and just removing it and then coloring everything else red. So this, that's C complement. Okay, and we come over here and let's pick a different color for A. Okay, so A So I've done A in green. Okay, so if I want to talk about everything that is in A that isn't in C, it's going to be everything over here, but it's not going to include this little piece of C. Okay? Likewise, if I come over here and I look at this over here, A intersection C complement, I think you can see that that's exactly the same area as well. Okay? Likewise, if we come over here, if we say, if we're considering all the x's that are not in C, that's the same thing as saying that x is contained in C complement. So I now have over here, x is contained in A, and x is contained in C complement. And that is the same thing as saying A intersection C complement. All right, so following up on our last example, we again return to an example in the book, and they ask us to construct a proof for the following. They say, show that A union B minus C is equal to A union B intersection C complement. Now, I think in the book they actually make this a lot more complicated than they need to. Okay? First of all, we know we already have a theorem that says to us that A minus C is equal to A intersection C complement. Okay? And I think all we need to do is just use this fact right over here. Well, this almost looks like that, but not quite. Why don't I come over here and do the following? Why don't I say, let D equal A union B. Nothing wrong with doing that. Then rewriting this, we get that D minus C is equal to D intersection C complement. Well, goodness, that looks just like that theorem over there, just where the A became a D. Okay, that's all you need to do for the proof. Book makes it complicated. Okay, I prefer simplicity. I'm not sure if this was in the book, perhaps I missed it, but it's a very important thing. I want to talk about counting elements in sets. This is actually very simple. And let me fix my pen here for one moment. Okay, now you may recall we said that if we have a set A, maybe that's the set A. We talked about the order of A, and we denoted it this way. And we said in this case that's asking how many elements are there in A. And in this case the answer is 3. And we said that you might refer to that as the order of A, or the magnitude of A. Now I want to consider another question here. Let's suppose I have another set here, B, and maybe this is equal to 4, 5, and 6. And the question I want to ask is what is the magnitude of A union B? Well, we can see in this situation A union B is equal to there's 6 elements in there. So this is equal to 6, which happens to be equal to the magnitude of A plus the magnitude of B. But now let's consider a different set. Suppose I had a set C, and suppose C had the following in it. Suppose C was 3, 4, and 5. Now, if I were to look at A union C, that's equal to 1, 2, 3, 4, 5. But here, if I were to ask you what is the magnitude of A union C, we can see that that's equal to 5, and that's not equal to the magnitude of A plus the magnitude of B. Well, we can see that the reason why that happened is because A intersection C is not empty. They have the same element in it, 3. And we can see this, again, if you considered just a Venn diagram. If they're disjoint sets, then we can see that the number of elements in the union would just be the sum of these two. But if they are not disjoint sets, if they overlap, if I add the number of elements in this set and I add the number of elements in this set, you can see that what I've done here, the intersection, which is right in here, I've added that twice. So in fact, what I need to do over here is I need to say that the order of A union C is equal to the order of A plus the order of C. And I just realized this is a mistake over here. This should be the order of C. And then what I need to do, because I've added the intersection twice, I need to subtract it out once. And I need to say minus the order of A intersection C. So we can make this into a theorem if you like, okay? And why don't we do that? I'll come over here and get a fresh page. And I'll say the following. If A intersection B is equal to the empty set, then the order of A union B is equal to the order of A plus the order of B. If A intersection B isn't empty, then the order of A union B is equal to the order of A plus the order of B minus the order of the intersection. Simple.